This is a hologram. Today we will discuss how a hologram can be created. Take a clear plastic sheet like the ones used for overhead projectors. Cut the sheet into pieces shaped like trapezoids. Then join these pieces together to form a pyramid-like structure with an open top. Next, search for any video labeled hologram video and play it on your mobile phone. Place the plastic pyramid upside down on the screen and dim the lights in the room slightly. View the screen through the sides of the plastic structure. You will see a wonderful floating three-dimensional illusion. The fascinating thing here is that the mobile screen, which displays two-dimensional information, appears as a three-dimensional hologram. This is a perfect example of how two-dimensional information can be converted into three-dimensional visualization. This brings us to a broader scientific discussion, our understanding of the universe and how we perceive reality. We believe we live in a three-dimensional world. The observable universe is also three-dimensional. However, what if this perception is not entirely accurate? What if the three-dimensional world we experience is actually a projection from a lower dimensional reality? This idea leads us to the concept of the holographic principle. We see a similar phenomenon in the hologram on a credit card. Three-dimensional-like images appearing on a two-dimensional surface. Scientists have mathematically shown that all the information about a three-dimensional object can, in principle, be stored on a two-dimensional surface. This raises an even deeper question. Do we actually live in a three-dimensional universe? Or is our entire three-dimensional experience just a projection like a hologram from a two-dimensional surface? This brings us to the contributions of two great scientists, Jacob Bekenstein and Stephen Hawking, particularly in the context of black holes. Stephen Hawking proposed that at the event horizon of a black hole, some fundamental laws of physics might be violated. Specifically, he pointed out a potential contradiction with the conservation of information, one of the core principles of physics. Hawking mathematically showed that when something falls into a black hole, all information about it appears to be permanently lost from the observable universe. In ordinary physics, even if you destroy a hard drive, the energy and information within it still exist in some form. It can, theoretically, be reconstructed. According to quantum mechanics, no information is ever truly lost from the universe. But Hawking's calculations suggested that black holes permanently erase information, contradicting this principle. This contradiction became known as the information paradox, and it posed a major challenge to physicists. They knew Hawking's mathematics was correct, but they also knew something was missing in the interpretation. Physicists Gerard 't Hooft and Leonard Susskind proposed a possible solution to this paradox. Later, in 1997, physicist Juan Maldacena provided a mathematical framework supporting this concept. They proposed that even if information seems to disappear inside a black hole, a perfect copy of all that information remains preserved on the event horizon, the black hole's two-dimensional boundary. This concept is the holographic principle. All three-dimensional information about what falls into a black hole is encoded on its two-dimensional surface, the event horizon. This principle may help resolve the information paradox and has become a key area of research in theoretical physics. In essence, our full three-dimensional universe could itself be a kind of projection, a hologram. In 1972, physicist Jacob Bekenstein derived a formula showing the maximum possible entropy, which is a measure of information that can exist within a given region of space. Interestingly, his formula didn't depend on the volume of the space, but rather on its surface area. This was surprising because you would expect entropy to scale with volume, but instead it scales with area. This insight led to a profound realization. As more particles fall into a black hole, its event horizon area increases to store the additional information. The event horizon acts like a kind of storage surface for all the information that would otherwise be lost. This confirms that Stephen Hawking was mathematically correct. Information appears to be lost forever from within the black hole. However, from the perspective of the larger universe, the information is not truly lost. It remains encoded on the black hole's two-dimensional surface, the event horizon. This is the core idea of the holographic universe, the principle that all the information describing our three-dimensional universe could actually be stored on a distant two-dimensional boundary, much like a hologram. This concept implies that any three-dimensional object or process could, at least mathematically, be perfectly described using just two-dimensional information. Similarly, a two-dimensional image could be reconstructed as a three-dimensional object, just like the holograms we see on a mobile screen. What does all this mean? It raises the possibility that our entire universe is actually a two-dimensional projection, a giant hologram, which appears to us as three-dimensional. Alternatively, could it be that our universe exists inside some vast black hole, with all of its information stored on the black hole's event horizon? At this point, we do not have a definite answer. It might be true, or it might not be. If you'd like to know the relationship between the world's most precisely defined sphere and the definition of a kilogram, you can check out a video on this topic. And if you enjoy the content, don't forget to subscribe to Science Sphere.